Hi, in this video we'll talk about convolutions. First we'll start with a mathematical definition, then we'll go through some examples of the convolutions in image processing, and then we'll talk how it works in convolutional neural networks. This is the convolution formula, and let's go through how we read this integral. So there are two functions. The first one is a single function, which is there, and the second one is so-called kernel function. So for the simplicity, let's take just a square function, j of x equals 1 if x is between 0 and 1. So essentially it's just a square signal with width 1 and the height also 1. So to calculate the convolution between those two functions, we need to multiply the values of those two functions along the entire axis, and the covered area would be the value of the convolution is just in one point. So we put the kernel function there, everything else is 0. We multiply them together, which is very easy to do because it's just 1. So the output function would be this, and the covered area is this. So just roughly I would estimate the output value as something around 2.5 maybe. And this is just one point where x equals 0. Now in the other points, we repeat this step with only difference that we shift our kernel function a little, and so on. Now let's see the animation of the convolution performed along the entire x-axis. And as you can see that our step function, what it does is just calculating the average within this window. But we can use the other kernels to get the other effects, and let's use Gaussian curve. So it will apply Gaussian blur on the original signal. So as we can see that Gaussian blur blended out the small details on the signal, and we are losing those small peaks. But what's good about the convolution, if we know what was the original kernel, we can invert it if we apply the inverse kernel. So in other words, if we have the signal and we know that it was blurred by something and know what the kernel was, at least we guess as much as we can, we apply it and we can recover the original signal. So for Gaussian blur, the kernel would be, assuming this is the line, so this is 0 on y coordinate, it will be something like this. Small peak inside and negative values on the sides. And as you can see, it kind of recovers the original signal, but let's compare. And they look pretty close. Let me zoom in. So this area is zoomed in here. But what about image processing? For image processing, instead of input function, we have input image, which is just a matrix. And the input values inside this matrix are from 0 to 255. 0 is black, 255 is white, and we have a small convolution kernel matrix. By the way, on this diagram, both images are small, but in the reality, the input image obviously can be quite big, up to a few megapixels, but the convolution matrix is usually quite small, from 3 to 5 pixels. So it's not going to be like 50 or something. So let's define our input image, and let's put 255 here, 255 here, and so on. Yeah, so sort of a circle. And let's use the convolution kernel that we already discussed, just averaging all the pixel values. So it's gonna be 1, 1, 1, everything 1, and we multiply it to 1/9. So this is gonna be our convolved image. So as it's not a function anymore and we have discrete values, how it works, we put the sliding window over the set of pixels, and then we calculate dot product, and this gives us just 1 pixel value. So at this position will give us the convolution of this cell. Then we shift it and repeat until we cover all the pixels. Okay, so let's begin. So the first one has 1, 2, 3 white pixels. Everything is black. So let's calculate the value. It's going to be 3 to 255 divided by 9, and it equals 85. So this is gonna be 85. Then we shift it a little to the right, and we still have 3 pixels, so still 85. Then we move it to the next row, and it's gonna be 1, 2, 3, 4 pixels. So 4 multiplied to 55 divide 9 equals 113. So 113, and it's symmetric, we just fill up this value. Then we continue. So it was our second row, and this one is our third row, and it still has 3 pixels, so 85. We shift right, and it's also 55. Then we move to this position, and it's gonna be 4 pixels. So 113, 113. Then we move here. It's gonna be 3, 85, 85. And we move to the last row. It's gonna be, in the first one contains 2 pixels. So it's gonna be 2 to 255 divide 9 equals 56. It's gonna be 56. Here also 56. So this is our output image. It's pretty small, and also we have padding. There are different ways to handle the padding. That we can just extrapolate the values and put 85 to the neighborhood cells and so on. And in many cases we just leave it empty because we don't actually lose much information. So if the image is big, let's say a few megapixels, just one line of pixels just doesn't matter at all. So let's see some examples how the actual images with convolution look like. So let's take an image and convert it to grayscale. For RGB image processing, it would be almost the same thing, except we need to repeat the operation 3 times and then merge the image. But for simplicity, we'll just convert to grayscale and repeat this only once. So this is our input image. And let's use our favorite convolution kernel, where we just average all the pixels and see how the image will change after this operation. So yeah, we applied the convolution. Convolution has 1/9 in every cell, and this is the image, but here I put the source image how it was on zoom, so we can more easily see what changed. And this is a zoomed area of the convoluted image, actually this area with the windows. We lose the detail, so the image became more blurry, which is sort of expected. And this is just done by one simple operation. So let's go next. And instead of blurring, let's do sharpening. So what's different now? We have a peak inside, like we had with the function, and we have negative values around. The next example I want to show is a so-called Sobel operation, which uses two sequential convolution operations. As a result of Sobel operator, it extracts the contours of the image. And the first step of Sobel is extract vertical lines. And the second step, horizontal lines. And the third one, we calculate the magnitude, like edges x square plus edges y square. Yeah, so the first step is extract the vertical lines and the convolution. You can see how the convolution looks like. And now we see almost only vertical features of the images. And the second one is very similar. The only difference, we flip the matrix to 90 degrees. So it's rotated, and now we see only horizontal features. And here's when we combine both of them. So now the image consists of just the lines. Those were the cases where we manually define the kernel to do the convolution. But for convolutional neural network, as part of training, they find the optimal kernels to extract the features. So let's assume we have layers, like the first layer, input layer, then we have a few convolutional layers, then we have some max pooling. Let's discuss it later. What's that? Yeah, like this. So let's say this is input, this is conv layer, couple of them. It's gonna be a max pool. It's gonna be also convolutional. Max pool again. Couple more. And we have a, let's draw like this, a couple of fully connected layers and softmax. So this is sort of like a typical classification model for images. And what happens there? We have an input, it goes to convolution. Each of the layer, despite it like just one layer, in fact, it also has multiple kernels assigned. It can be 16. And what happens at the beginning, the dimensionality of the layer of the image itself is high at the beginning, and it's a relatively small number of features. But as we go to the end, the dimensionality reduces, but the number of features grow. So let's say it would be like 124 to 56 by the end. So how max pooling works? Let's say we have 4 inputs and just 1 output. And inside the layer, we have just one value as set to 1, and it will set as 1. If nothing is set as 1, the output would be 0. And it's not like it takes it from the entire layer. It just goes through like a sliding window and reduces dimension. So from the beginning to the end, it reduces also with the help of max pool. It can be also average pooling sometimes. And by the end of the neural network, usually there is a couple of fully connected layers just to make the classification. So fully connected, every neuron is connected to all other, and the output of this MLP, let's call it MLP block, the output is connected to softmax. Maybe not, but softmax will just convert it into probabilities, and the output of the neural network won't be either it's a cat or a beagle, and so on. The first few layers, they extract low-level features, so lines, textures, maybe some very simple structures like points of the specific shapes. Let's keep in mind that the kernels are very small, so it can pick some of the minimalistic shapes, but it's very limited of what it can recognize. So let's say if it's 5 to 5, maybe it can recognize like a hard-coded shape of like arrow or something. It's gonna be arrow, vertical arrow. But it cannot recognize a complicated structure, but it doesn't have to, because when it extracted lines and textures, at some point it will just on some level those lines become the inputs for the other convolutional layers, and now it can see, okay, there is a line on the left, and on the right also is a line, and there is horizontal lines, line here. So it will think, okay, so it looks like it's a box, and inside, like on the layer, it will think that okay, so there are lines, well, probably it's a box, and here it will be like simple structures like box, triangle, maybe an eye, and etc. For the end of the neural network, it will have like structures like a paw, an eye, I don't know, tail. So it will have more complex features, and we don't know what they are actually, because it's a black box for us. But we know that they are like a higher order objects that it detected, and MLP layer will try to classify it. So it will think, okay, so it has 4 paws, 1 head, and the head like animal head, and it has whiskers, and I don't know, the texture is fur. So okay, so probably it's a cat, or maybe it's a dog. So to figure if it's a dog, maybe the ears must be of a different shape. But they will be listed here and on the inputs for MLP, and it will classify what's that. So the output will just show like the concrete class. And why the convolutional neural network are so effective is because they use very small kernels, and when we train the layer, we just need to learn the number of features multiplied to kernel size. So if we have 16 kernels, we multiply it 3 to 3, because it's a dimension of the kernel, multiply 16. This is the size of the parameters we need to learn during training for this single layer. So the efficiency is because of the minimalistic structure, hierarchical processing, and ability to accelerate it on GPU. So that's how the convolutions became so dominant in computer vision. And in general, as you can see, some simple principles like let's apply the kernel can lead to very complicated processing. So let me know if you like this video, experimental one. Let me know if you want to see more, and of course, like and subscribe.